Welcome back from the break. Now we are ready to jump into the modeling. In the modeling we will start with electric machines and generators, and then we'll go to batteries and supercapacitors, and then talk a little bit about some links that we can find in hybrid vehicles that transfer power between components. When we talk about electric motors and also about generators, they are classified in different groups. Here we use 4 different groups. There are other classifications. We have DC machines, DC for direct current. We have synchronous machines. This group sometimes also include brushless DC motors. We have synchronous machines, we have reluctance machines. There are also other devices like stepper motors that are digitally controlled synchronous machines. And we have ultrasonic motors that you, for example, can find in lenses for cameras. Electric machines is a topic for a separate course. We have the course TSFS03 Electrical Drives that discusses the machines in more details. When we talk about electric machines, we have 4 different quadrants where we are operating. The normal quadrant is up here where we have positive angular velocity and we have positive torque. That means that we are driving the vehicle forward with the electric machine. If we have negative torque, that means that we are braking. And we can also do reversing. So we can do reverse braking or we can do reverse driving. So with the negative torque we try to go backwards, and the angular velocity is also negative, so we're going backwards. And during this part here we are doing a deceleration since we're going backwards, but we have positive torque. The first machine that we have is a brushed DC machine. It's not used very often in electric vehicles or in hybrid vehicles, but it explains the basic principles. It's used, for example, in racetrack vehicles if you have played with them as a child. So the brushed DC machine works like this. The currents, through the currents cause a magnetic field in the rotor. The rotor is here, the stator is the things that we have around. The electric field that we have in the rotor here generates a repelling force to the pole here, and we also have a repelling force here. So it's rotating the machine like this. And the repelling forces continue here, and they are still continuing here, and we also have now pulling forces here that are trying to align the rotor to the field inside the machine. Here you see that we're about to switch polarity as we're doing now, and then the current reverses in the coils and we get the polarity here, so the cycle starts again. The pros and cons with this type of machine is that it's very simple to control. We just apply a voltage to these poles and it will start rotating. The drawbacks is that the brushes that are sitting here, these are called the brushes that are sitting on the connectors, they need maintenance. We need to service them. The characteristics of a DC motor has this simple characteristics. When we are increasing the voltage we get increased torque, but if the rotation speed goes up, the torque decreases, so that we get the operation along such a line, so that if we have an unloaded electric machine we can control the speed by controlling the voltage, and if we have a highly loaded electric machine we can control the takeoff torque with the voltage. So it's very easy to control, and that's what we have been doing when we're children playing with the electric racetracks. We're just controlling this voltage down to the rails of the electric racetrack. There is another machine that is called the Brushless DC Motor. This brushless DC motor solves the commutation and the brushes problem with the aid of a computer. So you have a computer that controls the windings of the machine. So we have a permanent magnet in the rotor in that case, and by employing different currents on the different coils we can get a rotating field here. With the aid of the computer we are rotating the field around here, and we're pulling the permanent magnets to follow that field. And there are specific devices that you can buy to directly control BLDC machines. The usage of DC motor is partly misleading because the source is DC to the computer, but the computer controls the electric machine in a more complex way. That's an alternating current. We are close to linear relations between current and torque and voltage and RPM. So here's an example of that close to linear relation. The next machine is Synchronous AC machine, which is essentially the same thing as a brushless DC motor, but they can, for example, be machines that are connected to the 50 Hz grid and get a rotational frequency that is proportional to the grid frequency. Finally, we have an asynchronous DC machine that's also called induction motor. The basic principle is that the stator here has a rotating magnetic field that has the effect that it's magnetizing the rotor, that also has a sequence of coils here. There is something that is called a squirrel cage if you look at the animation out to the right here. So the field here induces a field in the rotor in the squirrel cage, and with the induced field in the rotor you get the rotor to act as a magnet, and then you're rotating the field and pulling the rotor with you. The frequency with which we are rotating the field in the stator will cause a rotational speed of the rotor, but the rotor is not following exactly this speed unless we're operating more or less frictionless. If we load the rotor, there will be a small slip. The deviation between the rotating field and the rotor speed is called slip, and this slip controls how much torque can be transmitted, and that we'll see on the next slide here. Here they are rotating synchronously, and down here we are braking, so the rotation of the rotor is faster than the rotation of the field in the stator. And in this case here, the rotor is standstill, and we are starting it, and we have this breakaway torque, and then we have a maximum torque up at the design point here until it drops to the point where it's rotating synchronously or without any load at all. Another machine is a switched reluctance machine that is rotating with aid of using the reluctance effect. So the basic principle is that when we have magnetic material, they try to align as much as possible to get the best reluctance, so we have the best magnetic flow. And the way it's controlled is we're magnetizing this part here and it aligns like this. Next step, we magnetize this one and we're pulling that guy up here. And in the next step, we are magnetizing this and pulling that guy over there. So in this way, we can control the rotation by just having access to the reluctance. We don't need to have a permanent magnet. We need electrical fields and we need magnetic material. There are various electrical machines in hybrid. Mostly we have permanent magnet synchronous machines and induction motors, and people are talking now about switched reluctance machines. These are interesting as they don't need to have rare earth metals like neodymium for magnets. The AC motors compared to DC motors are less expensive, but they require more sophisticated control electronics, and that gives a higher overall cost. But the main advantage is once again that the brushed DC motor requires a lot of service in terms of the brushes. The other advantage, of course, that is very important for hybrids, as weight is important for hybrid, is that they have higher power density and higher efficiency. When we're looking at AC motors and compare the permanent magnet versus induction motors, we see these data extracted from the advisor database of permanent magnet motors and induction motors. We see that the permanent magnet motors of that database is higher than the induction motors, and we see that the induction motors have slightly higher power density. So there's not a trivial optimum. This one wins in terms of efficiency, while this one would win in terms of weight for the vehicle, which is also important for fuel economy. Now we have come to the point when we jump into the modeling of the devices. The modeling of the devices is mostly done using efficiency relations. Now we have come to the modeling of the electric machines. The modeling is mostly done by considering power, where we have the input power and we have the delivered power. If we are operating it in driving mode, we are inputting power here and then we multiply by the efficiency. But in the QSS thinking, we come from the output and then we need to divide with the efficiency. When we go the other way around, when we're going regenerative braking, we are getting power from the driveline and we multiply it by the efficiency of the device to get the power that is transmitted to the power electronics. These efficiencies are described in lookup tables or in maps or as separate models. And you can use, for example, Willen's line to capture low power performance. Examples of how these efficiency maps can look like: we have the first quadrant map for an electric AC machine here, a permanent magnet synchronous machine, and we have the induction motor, the synchronous AC machine here. In these graphs we have the torque, we have the rotational speed, and we have limitations of the operation here. So this is maximum torque, and then we have maximum power line, or in this case maximum speed. In the induction motor we have the maximum torque, and then we have the maximum power line. That are limitations of the electric machine. So the things that I want you to remember about both combustion engines and about electric machines are that the performance is described using these kind of maps where you have efficiency lines, and much of the control designs try to exploit the sweet spots in the different devices. For hybrid, it was mostly getting access to the sweet spots in terms of the combustion engine efficiency. But for pure electric vehicles, it also becomes important to design them so that we have access to the highest efficiency of the electric machine. But you see here that the highest efficiency are attained up at higher loads. They are not attained down at low loads or low speeds for none of the machines. Usually much attention is placed on the first quadrant, while when we do regenerative braking we also work in the second quadrant. Traditionally the first quadrant is well documented and you have supplier information for the efficiency. So when we have this electric motor drive, we're working with it in this region, while if we have electric generator load, we're working with it in this region. And suppose that we have gotten the supplier information from this well documented mode, but we want to use it for regenerative braking. How do we determine this generator mode? There are three methods. One is to mirror the efficiency map, so that we just say that the map in generator mode is the same thing as in the motor mode, but with negative torque. So we just make a mirroring in the speed line. So we mirror from top to bottom. The other method is to calculate the power losses and mirror the power losses. That does not give a symmetric map. The third approach is to use a Willen's approach to model the device. A machine that has been measured in both quadrants has shown this behavior. Once again, we have the highest efficiency out closer to the maximum power line, and for the generator mode we see that the best operating points are not attained in the same place, and it has lower efficiency in the generator mode. These models were fairly simple in terms of that we're working only with the efficiency and we're modeling the power losses. This is motivated in this course because we are focusing very much on fuel economy and learning the basic principles. There are much more advanced models that use component knowledge like inductance of the coil, resistance in the windings, and build physical models. In the book there are also dynamic models developed that can be used to understand the fields and how they evolve while you drive an electric machine. To give you some examples of motors that you find in devices near us, for example, a regular DVD player, when you take it to pieces you can find that it has three different types of motors. You have one normal DC motor like the racetrack that is used to open the tray. That one is selected because it's no precision and efficiency is not important, so the simplest possible technology is used. Then there's a BLDC motor that drives the rotation of the disc. This one is more performance, it has to rotate with a quite high angular velocity. Finally, there's a stepper motor that controls the positioning of the laser head. The next step in the walkthrough is to look at batteries and supercapacitors. These are used to store energy, for example from regenerative braking, that can later be used for accelerations or for driving. Batteries are energy storage devices where energy density is important, and for performance of the vehicle you know that the acceleration performance, the gradability, was coupled to the power, and that's why the power density becomes important. And durability is also important because we don't want to exchange the battery, since the battery is so expensive. That's why you see the evolution here, and you see that the lithium-ion battery that's most popular right now outperforms most other technologies in terms of these performance factors. It has both longer lifetime and higher energy density and higher power density. So this motivates why you see so much talk about lithium-ion batteries in the media right now. One challenge with lithium-ion batteries is that they can explode if you mistreat them. I will not talk about this in this lecture, but there will be another lecture after Easter where we'll talk more about batteries and different chemistries and the properties of batteries. When we model batteries in terms of the QSS framework, we come with the power requirement or regenerative power from the power electronics and from the driveline. This comes into the power electronics that is controlling the battery, and in the QSS thinking we have access to battery information where the voltage is coming here, and since we're looking at output power, this output power is generated by the product of the current from the battery and the voltage from the battery. So when we have a certain power requirement coming here, that gets translated to a current requirement that goes into the battery. And the battery then keeps track of the electric charge Q that we have in the battery. And the models have three components. The first component here is the power of the battery, where the power of the battery is used to determine the current. And then this voltage that is used here is coming from the state of charge, SOC. And there's also current dependence on how much voltage we have from the battery. And the third is the integration of the current, so that we're integrating this current to get Q as we do here. So finally the state of charge is related to the total amount of charge that we have in the battery in relation to the current amount of charge that we have. So the more charge we have, the higher SOC. We max out so that SOC is equal to 1 if we are fully charged, so this represents fully charged battery. An important battery is a lithium-ion battery, where we are using lithium ions, where we take them from one side while we're charging and we place them in layers of graphite, and then when we discharge they go the opposite side. I will talk much more about batteries in a separate lecture, but for now we need to have a model that you can work with in the next hand-in assignment. We will stick to this simple model where we will have a voltage source and there is an internal resistance inside the battery, and the terminal voltage depends on the open circuit voltage. This open circuit voltage comes from that it's the voltage that we can measure here if we're not taking out any current. If we're taking out a little bit of current, this will start to reduce the voltage that we see at the terminals. So this is the basic model that you will use in the hand-in assignment. You need to account for the inner resistance so that you account for the power losses that we have. Then we will have simple relation for the open circuit voltage. We will not look at open circuit voltage variations, but you must be aware that they are present in electric vehicles. In the next slide we will look at how this terminal voltage changes when we start to apply different currents over time. So we will start with the fully charged batteries and then we'll see how does this voltage react. So in the beginning we start here, it's fully charged, and then when we start to apply a low current, first it drops quickly, then we get out to a point here where it drops more slowly. If we increase the current, we get a higher initial drop and then it ramps down more rapidly. And finally, with even higher, we go down more. So we can see higher current has two effects. We get the resistive losses, which are seen as a difference, partly the differences between these lines. And then the higher current will also drain the battery quicker. And therefore we have higher slopes here. So in this axis here we have the time, and this is not absolute Q0, but it's fully charged here, and then we're depleting it, and somewhere out here the battery will be emptied by this, and with this earlier, and this higher current even earlier. We can also look at more advanced models for batteries, and these are equivalent circuit models, where the simplest model is just a perfect voltage source. The next model that we're using in the hand-in assignments in this course is a perfect voltage source with an internal resistance. Then you can add dynamic components that relate to the inner chemistry of batteries. You can also add inductors that capture that the batteries are not perfect. And when you are doing more physical modeling, you can find even more advanced models and place components in relation to the different materials that you see inside the batteries. Here we have an important part concerning the state of charge estimation and concerning the relation between the state of charge and the voltage. So we have the voltage, and here we have the state of charge, here measured in ampere hours. So here it's empty and here it's full. And these are related to that we're pulling current out, so we're emptying the battery. And we're counting how much charge we have pulled out from the battery. State of charge is related to the amount of charge in the battery. And one way to get this curve here is to do what is called Coulomb counting, that we're counting the amount of charge that we have drained out. These are two different batteries that have been discharged at 3 different currents. So have the top two here that have been discharged with 6 amperes, and that one has 6 amperes, and the next one is 12, and the final ones are at 18 amperes. The things that I want you to notice is that we see the effect of the inner resistance of the two different batteries here by the difference between the 3 lines for the 3 different currents, and then you see the state of charge versus the voltage effect. One interesting part here is related to the state of charge, the estimation. For some batteries there is not a strong relation between the voltage and the state of charge. Like if you look for this or this or this, you cannot, by just measuring the voltage, see what is the state of charge. In this case you need a combination of doing Coulomb counting and looking at the voltage to mix these into a number that tells what the state of charge is. Another example of a discharge profile with another battery chemistry is seen in this graph. Here we have done discharging and then charging and discharging and charging over 2048 cycles over 550 days. And the aging effect can be seen here, where the capacity of the battery is changing. And when we reach end of life, the capacity has decreased significantly. In this case I just illustrated it with 60% reduction of the battery capacity from the start here. Normally people are using 80% as the end of life. When it comes to estimating the state of charge, we have 2 challenges. One is that the voltage curve can be flat, and the other is seen in the coming slide. In the next slide I will extend this part of the plot where we'll look specifically at what's happening here when we start to charge and when we come back again. So we had 2 challenges with the state of charge. One was that it might not be easy to detect the voltage change. This chemistry is easier, but the other chemistry was more difficult. But this illustrates something else, that if we do not do any coupling between the voltage, if we only rely upon Coulomb counting, then we can get a drift. So we're not coming back to exactly the same place, but we're coming back to another point, and the charging inefficiency is then the cause of this part here. All charging cycles have been reset to start here. They come up to different points. If we do not do this reset here, we can get this drift. This drift is caused by the losses inside the battery. And if you look at the current and if you look at the charge, it represents that for every cycle 2 times 10 to the power of 20 electrons are lost. They are not lost physically, but they do not do the electric work that they are supposed to do to increase the potential inside the battery. Now I've talked about losses inside the battery. So then you could ask the question, what is the efficiency of a battery? Efficiency of batteries is a bit problematic because it's not an energy converter. When we have energy converters, then we can easily define efficiency. We measure what goes in and measure what goes out. While we have an energy storage, we are inserting energy at the charging instant, and then at a later instant we are extracting the energy. So we cannot look at the instantaneous efficiency of the device. The total efficiency over a complete cycle we can do calculations of, but the losses will depend on the cycle, and we will talk more about that in the specific lecture. So I am advertising a battery lecture that will be provided. This is motivated by the fact that batteries are an important component in the future of electromobility, and therefore we will have this separate lecture devoted to batteries that will be made available after Easter. Another way to store energy is to use supercapacitors or ultracapacitors. They have high power density and they can be used as short timescale energy buffers. They can also be used to do load leveling to the batteries. With their capability to quickly take up charge, they can reduce the currents that are delivered into the battery. They are very similar to batteries in terms of modeling, and in the circuitry you exchange the ideal voltage source for a capacitor, and you can then work with the open source voltage, which will depend on the integrated current. Concerning efficiency of capacitors, they are the same as for batteries. It's problematic because the efficiency will depend on the cycle over which we're using it. The final part of the lecture touches transfer of power, both electric and mechanic. In the electric system we have Powerlinx. For example, the battery is a DC component, and we can also in a vehicle have several battery packs, perhaps even at several DC levels. Finally, the grid is an AC system, so there is a need for transforming between them, and we need these electrical glue components. The grid is also an AC system if we start to look at electric vehicles or plug-in hybrid electric vehicles. To connect these systems together we need some electric glue components. We need DC-DC converters to connect between different battery systems and potentially also between capacitors and batteries. We need inverters, both those that are going from DC to AC when they are running the AC electric machines, and also from AC to DC when we do charging, or bidirectionally if we are doing regenerative braking. Modeling of Powerlinx is usually done by modeling the power losses, and for example using Wilhelm's line models where you have an asymptotic efficiency that's fairly close to 1, and you have a loss which is connected to just keeping the electronics alive while we're idling. We also have torque couplers like mechanical glue components, and these can include gears. We can have gear sets that decouple the angular velocities from each other. We can have planetary gear sets as in the Toyota Prius. We can have clutches to engage and disengage components. The basic equations and models for these is that we're working with angular velocities that we extract from the geometric gear ratios. And we have torque transmission that we get from a combination of the previous angular velocities and from the power balance over device. Then we can add submodels for friction and other losses in the component. Finally, we have power split devices that we have already covered in the Toyota Prius. They manage the split between different components, and they are an important component when we want to achieve the flexibility. For example, having the ability to place the engine in its best operating point. The modeling approach here is the same, that we use speed relations and then we extract the torque from the power balances on the device. It's also possible to add more planetary gears. For example, Prius Generation 1 had only one planetary gear, while Prius Generation 2 has 2 planetary gears, and they have also added a torque lockup feature to the planetary gears to improve the efficiency, so that you don't need to have that generator loop as you had in the Generation 1 Prius. So, with this we call it an end. We have gone through the introduction to hybrid electric vehicles with the different configurations and with the different components that we need to model to go to electromobility. And with that, I say thank you for listening in on this module, and hopefully you can meet me at 5 o'clock when we have the next session for discussing the material. So, see you. Bye.